So this is another set of past questions. Let's start with question number 1. This is episode 2. So question number 1, they said which temperature value is referred to as absolute zero? You should know by now that absolute zero is either 0 Kelvin or minus 273.15 degrees Celsius. Always mark this minus, it's important for absolute zero temperature, and the pressure in absolute zero is 0. Below the absolute zero, pressure is negative. So yeah, they said which temperature value is referred to as absolute zero? That's option C, minus 273.15 degrees Celsius. Sometimes they might also put the answer in Fahrenheit, so you just need to convert your degree Celsius Fahrenheit. Let's do that. Now TF is equal to 9/5 times minus 273.15 plus 32. So that will be in degree Fahrenheit. Our absolute zero in degree Fahrenheit. I'm just doing this one. In degree Fahrenheit, our absolute zero is 9 times minus 273.15 divided by 5 plus 32. So in degree Fahrenheit, our absolute zero is 4 minus 459.67 degree Fahrenheit. That's our absolute zero in Fahrenheit. So in Celsius is minus 273.15 degrees Celsius. In Kelvin is 0 Kelvin. In Fahrenheit is minus 459.67 degrees Fahrenheit. You can bring it out, so don't miss it when you see it. Question number 2. Question number 2, they said on temperature scale, the ice and steam point are 20 and 110 respectively. That's on temperature scale A. On temperature scale B, the ice point is 45. Let's draw the one on scale A. Scale A, they said the ice point is 20 degrees, while the steam point is 110. On scale B, the ice point is 45. The ice point is 45. If when the temperature of an object on scale A is 50, and on scale B it is 70, what is the steam point of scale B? So they're asking us for a steam point of scale B. So anything we do here, we do it here. So that will be 50 minus 20. This minus the lower fixed point over upper fixed point minus lower fixed point. That's 110 minus 20. We'll do the same thing here too. That will be 70 minus 45 over x minus 45. X minus 45. So let's simplify that. This one will be 30 over 90. Because 70 minus 45 is 25. And 5 over x minus 45. So x minus 45. So that will be x minus 45 is equal to, if we multiply, we cross multiply, that will be 90 times 25 divided by 30. That will be 75. That's if we cross multiply this. Just say 90 times 25 divided by 30. So x will be 75 plus 45. And that's 75 plus 45 is 120. The answer is 120. And that's option A. That's option A. The answer is 120. So question number 3. It says which of the following equation for conversion of temperature in Kelvin to Fahrenheit? That means we want to convert Kelvin to Fahrenheit, and they're asking us what's the formula. What's the formula to convert Kelvin to Fahrenheit? So we all know to convert from Celsius to Fahrenheit, it is TF is equal to 9/5 TC plus 32. But they're asking us if one converts from Kelvin to Fahrenheit, so what do? We all know that Kelvin is TC, like Celsius plus 273. So that means Celsius will be Kelvin minus 273. As if you bring the 273 here, that will be Kelvin minus 273. So we'll put this Kelvin minus 273, we'll put it inside this Celsius, because they're not asking us for Celsius, they're asking us for Kelvin. That will be 9/5 bracket Kelvin minus 273 plus 32. And plus 32 is outside. So if you look at the option, that will be 9/5 Kelvin minus, if we multiply 9/5 times TK is 9/5 Kelvin. They also multiply 9/5 times 273. That's 273 times 9 divided by 5. That's 491. 491.4. 491.4. Then plus 32. This here. So degree in Fahrenheit will be 9/5 TK. That's minus 491.4 plus 32 is, that's minus 459.4. So this is the formula if you want to convert Kelvin to Fahrenheit, and that's option B.
Don't pause it.
Question number 4. Is which of this is not a thermometric property? E. Resistance. Resistance is a thermometric property for resistance thermometer. EMF, electromotive force, is also a thermometric property. Color of an object is also a thermometric property. That if you are dealing with this thermometer, optical pyrometer. And option D, temperature. Temperature is not a thermometric property. So you should know that one. That temperature is not a thermometric property. So question number 5, he said the unit of coefficient of volume expansion is, and actually for the unit of cubic expansivity. The unit for linear expansivity, area expansivity, cubic expansivity, everything is per Kelvin or per degree Celsius. That is like per degree Celsius. Everything is per Kelvin or per degree Celsius. Both linear, area, volume, everything is. So the answer is per Kelvin, and that's option B. So question number 5, he said, for which of the following processes is there a change in inter-energy when a system is taken from one state to another? A, they said adiabatic free expansion. In adiabatic free expansion, the change in inter-energy is 0. So they are asking us which one is there a change in inter-energy. In adiabatic, there is change in inter-energy. In isothermal, change in inter-energy is 0. Change in inter-energy is 0. In cyclic process, change in inter-energy is also 0. So if you look at option A, adiabatic free expansion, yes, change in inter-energy is 0. So that's not our answer. B, cyclic, change in inter-energy is also 0. Isothermal, because inter-energy depends on temperature, and isothermal is constant temperature, that means inter-energy will be constant. So change in the inter-energy will be 0. Because if anything is constant, the change in that thing will be 0. So that's not our answer. Option D, adiabatic, yes. Change in inter-energy in adiabatic is not 0. But in adiabatic free expansion, change in inter-energy is 0. But in ordinary adiabatic, change in inter-energy is not 0. So answer is option D for question 6. Question 7, they said when a gas is isothermally compressed, the work done by the gas is, when we compress a gas, we do work on the gas. And if you do work on the gas will, the work done will be negative. Because the gas is compressing, so the work done will be negative. And if something is negative, that means it's less than 0. So our answer will be less than 0, and that's C. So when the gas is isothermally compressed, the work done by the gas is less than 0. Number 8. They said how many moles of oxygen will its internal energy change by? Internal energy is 149.58 joule. So how many moles of oxygen will its internal energy change by 149.58 joule when its temperature is increased by 4 Kelvin? Now the change in temperature is 4 Kelvin. And they gave us R to be 8.31 joule per mole per Kelvin. So they're asking us to find number of mole. And we all know that internal energy is NCV, and it's NCV change in T. NCV change in T. So we are looking for N. But you know this CV is the specific heat capacity at constant volume. And for monoatomic, it is 3/2R. But oxygen is not monoatomic. Oxygen is diatomic, O2. Oxygen is diatomic. So, and for diatomic, the CV is 5/2R. So let's put that together. That will be internal energy will be 149.58 is equal to N. We are looking for it. CV 5/2R. 5/2. What's our R? 8.31. 8.31. That's times 8.31 times 8.31. And our change in temperature is 4 Kelvin. That's times 4. That will be 149.58 is equal to N times, let's calculate this one, as 5 times 8.31 times 4 divided by 2. That's times 81. That's times 81. So our number of moles will just be 149.58 over 81. Our number of moles will be 149.58 divided by 81. That will be 1.5. That will be 1.5. That will be 1.5. Our answer is option C. Looking at it, our answer is option C. So our answer is option C. Question number 9. They said one of the assumptions of the kinetic theory of gases is that momentum and kinetic energy of the gas molecules are conserved. This assumption means that the collision among the molecules are. So if the momentum is conserved and the velocity remains constant, if the momentum is constant and the kinetic energy is constant, that shows that that's an elastic collision. Because in kinetic theory of gas, the gases collide and energy is conserved. That's kinetic energy is conserved and momentum is conserved. That shows us that that's elastic collision. So the answer is option D. So question number 10. They said 2 moles of a gas expands isothermally, okay, from a state for which the pressure and volume are, the initial pressure and volume is, pressure is 8 atmosphere as P1 is 8 atmosphere, and at 10 centimeter cube, that's V1 is 10 centimeter cube respectively. So another state for which the pressure, that's P2 is 2 atmosphere. If the work done during the expansion is 8 kilojoule, and if the work done is 8,000 joule, that's 8 kilojoule, that's 8,000 joule. What is the temperature of the gas? And we all know that for isothermal expansion or compression, the work done is nRT. nRT being V2 over V1. So, and here they gave us P1, they gave us V1 over P2. So we can just use Boyle's law to find V2. Then we'll do V2 over V1. But there's this other equation that is nRT. It can also be nRT ln P1 over P2. So instead of using volume, you can just use pressure. So here they've given us P1 and P2, so we don't need to find V2. We don't need to go through the Boyle's law route, find V2, then put it. You can just do P1 over P2. So let's do it like that. So work is 8,000. We got N2, R is 8.31. That's our constant, times nRT. So it's temperature they say we should look for, times, let's close up, times ln P1 over P2. That's 8 over 2. That'll be 8,000 is equal to 2 times 8.31. 2 times 8.31 times T times, that will be ln 4. So ln 4 is 1.3863. 1.3863, yeah, 1 times 1.3863. So let's just divide everything. Let's just do, so temperature is at T will be 8,000. That's 8,000 divided by 2 divided by 8.31 and divided by 1.3863 divided by 1.3863. That will be 347.2 degrees Celsius. That's 347.2 degrees Celsius, and that is option B. So to verify this answer, you can also pass through the Boyle's law. The Boyle's law, P1 V1 is equal to P2 V2. Then you use this information here, P1 V1 is equal to P2. Then you find V2. Then you use V2, use this equation, then solve it. If you get the same thing, just to show you that you can also use this equation. So you can do it after this video.